For those of you who paid some little attention on this, the table of characteristic peak, you might have noticed that. Look at those three guys. Okay, all of them they belong to stretching vibrations of CH single bonds. All of them are CH single bonds. Okay, all of them are stretching vibrations. Okay, why you see they are stretching, the vibration frequency. They vary and in a systematic manner. And for similar degree, you will see the CO stretching vibration. We are talking about single bond only. Okay? If the carbon is sp2 hybridized, it's 1200. And if it's sp3 hybridized, then the stretching vibration is somewhere around 1100. Okay? Actually usually below 1200. Why that's the case? Okay? And to understand that, I would like to introduce a mechanical model. When we consider the stretching vibration of a chemical bond, we can treat it using a ball and a spring model. So basically, this is a chemical bond. The M1 and M2 are the masses of the two atoms participating in chemical bond. Okay? And the bond strength, okay, can be represented by a constant called K. So the stronger the bond is, the greater the K will be. And M1, M2 is straightforward. Basically, the heavier the atoms are heavier, the M1, M2 will be greater. Okay. So the stretching vibration of this kind of bond can be modeled using a spring and the beads model. So you can consider two atoms or two beads have the corresponding masses of the two atoms, and the two atoms, the two beads, they are connected by a spring, just like two atoms connected by chemical bond. So the strength of the chemical bond can be represented by spring constant of the spring K. Okay? So if you have this assembling of beads and the spring, you pull it, you'll start to undergo stretching vibration. And the stretching vibration frequency can be represented by this equation, equal to 1/2 pi times in the radical K divided by mu. K is the spring constant. Mu is a term called reduced mass, is equal to M1 times M2 divided by M1 plus M2. So I'm not asking you memorize this exact equation. Instead, you want to see the trend. Okay, so if the two atoms, if you keep the two atoms the same, okay, you don't change the atom. Okay, you just change the bond strength. Means the mu remains as a constant, right? Two atoms you don't change it, then this term would be constant because this one is just related with atom mass. So if you don't change the two atoms at all, this would be a constant. Okay, pi is a constant. So if you change the bond strength, what you can see is the stronger the bond is, the stretching vibration frequency goes up. And the weaker the bond, the K will become smaller, and the stretching vibration frequency also goes down. Okay, so that's the first thing. The stronger the bond is, the greater the frequency. Okay, the weaker the bond is, the lower the frequency. Okay, this is the one. Okay, the other thing is if you keep the K as a constant. Okay, then if the mu is greater, the frequency will what? If this one increase, the frequency will decrease. Okay, so the heavier the atoms are, the lower the frequency. That's the qualitative relationship I ask you to establish. That's a requirement. Okay, so you have to know the stronger the bond is, the frequency goes up. Okay, stretching frequency. I'm talking about stretching frequency, stretching vibration frequency only. Okay, stronger the bond is, the frequency goes up. The heavier the atom now, the frequency goes down. Now you look at it, those kind of CH single bonds, all of them are single bond, okay? But the bond strength is related to the hybridization state. As we learned earlier, sp2 carbon generally form a stronger bond than sp3 carbon, and sp carbon form a stronger bond than the sp2 carbon. So although all those three are single bonds, this single bond is the strongest. This one is the second. This one is the weakest. So that's why you see their vibration frequency vary in this manner. Because if we compare the vibrational frequency of those stretching frequency of those three bonds, three kind of single bonds, we don't change the type of atom. They remain the same, carbon, hydrogen. Okay? All of them are single bonds. However, we change the bond strength because the bond strength is related to the hybridization state. We learned in Organic 1. If you don't recall, go check the Organic 1, chapter 9, alkynes. Okay, sp-CH bonds are stronger than sp2-CH bonds. sp2-CH bonds are stronger than sp3-CH bonds. Okay, so that's why they have this kind of vibration frequency, systematic change in the vibration frequency because bond strength is different. Same argument, sp2-CO bond is a bit stronger than sp3-CO bond, although both are single bond. That's why stretching frequency of sp2-CO is a bit higher than sp3-CO. So this is something I do ask you to understand. Okay. Now, just with knowing this, we can just I'm gonna ask you to so out of those 5 bonds, I'm asking you to tell me which one has the highest stretching vibration frequency. Huh? CO. Well, first the CO, correct? Because of the CO, that's the bond of the lowest mass atom, right? But which one? We have CO double bond, CO single bond. See, if you compare CO single bond, CO double bond, okay, the masses are the same, right? Both ends you have basically, carbon and oxygen bound together. Masses are the same. Differences, what's the difference? The bond strength, right? So which one is stronger, has a stronger bond? CO double bond or CO single bond? Double bond. So obviously, out of these two, CO double bond should have a higher frequency. See, let's look at two things. And masses of atoms. The CO already, they are lightest atoms here. Okay? Then, out of two CO bonds, you look at a stronger bond. CO double bond is, in theory, almost double, twice as strong as CO. Not exactly, but almost. Okay? So that's why the highest frequency. Which one is the lowest frequency? Stretching frequency? Lowest, you look at the heaviest. The atoms are heaviest. Yes. Huh? Yes, Si. Okay, because Si is the heaviest, atom, and also because only bond with Si is Sis. Okay, both sides are heavy atom, and also single bond. So the CO double bond should have the highest stretching frequency, and SiS should have the lowest stretching frequency. That's just something I ask you to make quality. I'm not asking you any computation, but you must be able to do the comparison. Similarly, if you have, let's say, CH, the sp2CH, sp3CH, and sp2cd and sp3cd. Okay, and the D is equal to H2. Okay, out of those four bonds, which one has the highest stretching frequency? Which one has the lowest stretching frequency? So we have four bonds, okay? sp2ch, sp3ch, and sp2ct, and sp3cd. D is H2, okay? So which of these bonds has a higher stretching frequency? Again, consider two things: bond strength and atomic mass. Jen, can you tell me which one has the highest frequency? Okay. Very good. Very good, very good, very good. Okay? Because sp3 gives you a weaker bond, right? sp2 gives you a stronger bond. So the highest one, you want a stronger bond and the lightest atom. So H is the lightest atom. So this strongest bond, the lightest atom is sp2. That's the highest. And this one, the weakest bond and the heaviest atom, lowest. So this is just the major goal for me to introduce this equation. I'm not asking to memorize the equation, just to have a concept of atomic mass and the bond stress and how these two factors qualitatively affect the stretching frequency. Okay. So that's about the infrared. And the next spectroscope technique is UV visible spectroscopy. So as we learned the absorption of infrared photons indicate that you have a transition between the vibration and energy state. What about absorption of a UV or visible photon? That indicates that you have a transition between the electronic energy states. And the electron energy levels, they are separated by larger gaps than infrared. So that's why large energy gaps than the vibration energy state. That's why their absorption they usually occur at a higher frequency region. They are correspond to ultraviolet, UV, or visible light. And the absorbance is a proportion to the concentration in the path length. You might have learned this one in general chemistry. Did you guys learn this? Epsilon equal to A divided by C times L. C is concentration, and the L is the path length. A is absorbance. Epsilon is called absorption coefficient. But that's not something we're gonna pay a lot of attention here. We basically here, we mostly care about the absorption wavelength. So absorption wavelength reflect the frequency, and you know that absorption frequencies depend on the energy gap between the two levels. So if you know the absorption wavelength, okay, and that is basically tell you information about frequency, okay, and the frequency comes from constant, that's equal to energy level, energy difference between two levels. Okay. So usually in for those molecules give you ultraviolet visible absorption peaks. Those absorptions are usually due to the transition between the highest occupied molecular orbital to the lowest unoccupied molecular orbital. So just for example, here we have called 1,3-cyclooctadiene. Okay? So the highest occupied molecular orbital is the pi orbital. Okay? And the lowest unoccupied molecular orbital also is a pi orbital, but an anti-bonding orbital. So the energy gap between these two orbitals is due to is directly corresponding to the wavelength of maximum absorption, lambda maximum. So basically, the transition from here to here, okay, will corresponding to energy of the photon absorbed to give this transition. So in this particular molecule, you will see the the UV visible spectrum look like this. So the in a UV visible spectrum, usually the y-axis either will be absorbance or absorptivity. So the absorptivity is calculated, from this equation. A is absorbance, C is concentration, L is path length. And the x-axis is not a frequency unit. Just historical reason, the for UV visible spectra, usually we use wavelength as x-axis. So just these are all historical reasons. We could have used the frequency, it's nothing wrong, but just hence got used to use wavelength, nanometer. So the most important thing we are looking at, at least in this particular section, we care the most is the wavelength at which maximum absorption is observed. So the peak absorption wavelength. So in this particular case, it's about a little lower than 230 nanometer. Okay. So in this case, there's the around 230 nanometer. So what this one the can tell us is that they tell us the energy gap between the HOMO highest occupied molecular orbital and the lowest unoccupied molecular orbital. And this gap is directly associated with the length of the conjugated pi system. Means how many double bonds you have in a completed conjugated pi system. It's not how many double bonds you have in a molecule, but how many double bonds in a sequence of completed conjugated pi system. So the more double bonds you have there, you're going to have a longer wavelength than the maximum. So here you can see the some the table of the pi conjugated molecules and their lambda maxima. Lambda maxima means the wavelength at maximum absorption. Okay? So what you can see is those two molecules both only has one double bond. Okay, they're not really pi conjugated. You can see some impact of the having LQ groups on the double bond can let the lambda maxima go to a bit longer wavelength. But the largest impact is you have two double bonds in conjugation. So those two double bonds are separate one common single bond. Okay, this called that's what we learned in chapter 11. We see those two double bonds are in conjugation. And then you see it's a large shift to the longer wavelength from 170 to about 220. Now you have see three double bonds, okay, this molecule, three double bonds in conjugation. You will see another further shift about 40 nanometers. Okay, and then the here you have how many? One, totally five double bonds in conjugation, and then you shift to about 330 nanometers. So the most important thing you will be learning here in this section is the lambda maxima means the wavelength maximum absorption directly correlate to the number of double bonds in a sequence of conjugate double bonds. The more double bonds you have in the conjugation, the longer, the lambda maxima you're going to have. One extreme you have here is this guy, okay? They call lycopene, okay? They actually observe about 450 nanometer because this guy has so many double bonds in conjugation. Can you tell me how many double bonds are in conjugation? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 double bonds in the molecule, okay? But how many of them in conjugation system? How many double bonds there are in conjugation? We have 13 double bonds in the entire molecule, okay? How many of them are in conjugation? How many double bonds do you have in the longest conjugate system here? It's 11, okay? The two n double bonds are not part of it, okay? So the absorption, lambda maxima determined by 11 double bonds. Those two double bonds, they are not relevant because they are not in conjugate with the rest of double bonds. So if we are going to give you just one exercise, let's say I give you a group of molecules, okay? So those are all polyenes, okay? So out of those three polyenes, okay, which one has the longest lambda maxima? Which one has the shortest lambda maxima? So A, B, C, okay? Which one has the longest lambda maxima? Which one has the shortest lambda maxima? Yes, he has the longest because he has 4 double bonds in the conjugation system. 4 double bonds in conjugation. Which one is shortest? Yeah.
I can't really tell because I don't know if what's connected on A or what's not connected on A, but I can say A.
Yeah, A is shortest because none of double bonds in conjugation. Because those two double bonds they share one carbon, they are not conjugated. Okay. What double bond is share in one carbon? See, this double bond and the other double bond, these two double bonds must be perpendicular to each other. Okay. So these two double bonds they are not in conjugation. Okay. If two double bonds share a carbon, so this one is shortest, this one is the longest. Okay. You have to count the number of double bonds in conjugation, not just count the number of double bonds. Okay. So it's unusually hard counting. Okay. Yeah. What did you say? So, could you say again?
Is there two conjugated?
No, there's a C. There's a 4 double bonds in conjugation. So 1, 2, 3, 4. 4 double bonds they are in conjugation. 4 double bonds they are connected together. No, terminal was still in conjugation of the rest. So basically, you have a system of 8 pi electrons, and in one conjugated system. Okay? Because those are, see, if you try to say, hey, let's say if you take say if you put the positive charge here, okay, you can all the way delocalize over here. Okay? So if it's one, because all those you have a sequence of 8 carbons, all of them sp2 hybridized. Okay, you don't have any sp3 hybridized carbon in the middle. So 8 carbons, all of them sp2 hybridized. So yes, this is a conjugate system with 4 double bonds. If you have 3, yeah. C have no conjugation. I mean, A has 0 conjugation. A has 0 conjugation. Okay, the last spectroscopic technique is called mass spectrometry. And technically, it's not a spectroscopic technique because we don't directly using electromagnetic radiation to going through our sample, but because of the provide similar information, not similar, relevant information to the molecule we're going to be looking at. So we learn this technique together with the rest of the spectroscopic method. So in most traditional mass spectrometry method, actually your sample will be first vaporized into gaseous state, then introduced in a vacuum chamber. Then you're gonna the instrument is gonna send a beam of high energy electron to hit your sample. And what happens basically, like here, you have atom, or molecule, then electron hit it, We all know electrons are much lighter than molecules. So what happens in such a collision? If a very small thing hit very heavy thing, the very small thing, the electron will be bounced, away, But this collision is going to transfer some of energy, kinetic energy, from the electrons to the molecule. So the molecule will be energized, go to an excited state, And then this excited molecule can eject an electron, and the molecule itself becomes something called cationic radical. Assume that our molecule is a normal organic molecule, means all the electrons are paired. So then if losing an electron, it becomes cation, and the original is paired, then losing electron becomes radical, called cationic radical. This kind of cationic radical has a name called molecular ion. So compared to the molecule itself, this guy almost have the exactly same mass because electrons, as you should know, the electrons almost have no mass. It does have a mass. It's about 2,000 of a proton's mass. An electron's mass is about 2,000 of a proton. But usually we consider the electron has very little electron mass, so we can forget about. So we say this kind of cationic radical has the same mass, not exactly, but very close. Same mass as a molecule, So we call it molecular ion. And then there's molecular ion, and the molecular ion, then you can let it going through a magnetic field. And then the magnetic field can have the interaction with the molecular ion. So what the magnetic field does is cannot be considered if molecular ion, they are the cars on the freeway, So they are moving at a certain speed. The magnetic field create a sideway force, So they're gonna just like drive on the freeway. They have a wind blow sideways. So those winds try to change the direction the molecular ion. So you can guess. No, not guess. One thing I can tell you: the interaction the magnetic field has on the molecular ion is directly related to the charge on the molecular ion. The force, the force only relates to the charge. So that means if you have many molecular ions, say A, B, C, D, all the molecular ions, all of them have the single unit of positive charge. So the force, the applied on those molecular ions from magnetic field, they are the same. Force are the same, but the A, B, C, D molecular ions, the mass are different. So you can guess, if you have all those ions move at a similar speed, so then the force, the sideway force applied to those ions are the same. So the heavier the ion it is, the less change the force will be you know, less change of moving direction will be observed on those ions. Just like, if you have two vehicles, one is a very, let's say, very compact, smart car. Is a smart car very small? Occupy a small parking place on the freeway, and the 18-wheel truck, okay, on the driving at the same speed, if the wind blows sideways, the very small cars will be influenced a lot more by the wind. And same thing here, you have molecular ion moving in the magnetic field. So the lighter ions will be deflected more by magnetic field than the heavy ion. So basically, the highest mass ions will be deflected least. The lowest, the ions will deflect the most. So this basically can separate. Depending on the degree of deflection, you can sort and calculate the mass of each ion. So exactly, uh, those sorting is based on called mass charge ratio. So if you go through a quantitative thing, you have to see the calculate the mass charge ratio. But in most of, over 90% of circumstances, we will see in small molecules, the charge Z always 1. If the charge Z always 1, the mass charge ratio is pretty much equal to the mass. Okay? So basically, the mass spectrometry, what mass spectrometry tells us is the mass of the molecule. So what a mass spectrum will show us, so the mass spectrum will look like the one we're showing here. The x-axis is the mass charge ratio. So because only those charged species can be detected, and on the over 90% circumstance, the amount of charge on those molecular ions always 1. So the mass charge ratio, for the time being, you can just understand as a mass number of the species. Okay. And the y-axis is just relative intensity. So that means because it is relative to the strongest peak we have here, okay, 100%. We also call the base peak. The base peak is the peak of the basically the highest intensity, 100% intensity. That's called base peak. Okay? And although the first kind of ionic species formed in a mass spectrometer is called molecular ion peak. But the base peak and the molecular ion peak, they could be different. Okay? But here, this example is a mass spectrum of benzene. And we know the mass number of benzene is what? Carbon, assume carbon is 12, hydrogen 1. We have C6H6. It's 78. Okay. So in this case, the base peak does have a mass charge ratio of 78. So it matches the molecular ion peak, but it's not always the case. Now, I hope you understand this peak is basically is the base peak is the molecular ion of benzene. Basically, benzene loses 1 electron, didn't lose any proton or whatsoever, so it gives you a peak of 78. Okay. Now the question is, if you know this peak is 78, but also you have a 79 peak and even 80 peak. 79 peak is actually pretty weak. 80 peak is even weaker. Okay. But why you have those small peaks above 78? Okay. And now to answer that question, we have to ask ourselves how this 78 peak come from. Okay. 78 peak, we have this 78 peak because carbons are mostly carbon 12. Okay. So each carbon is 12, 6 carbon 72. And the hydrogen, most of them are hydrogen 1. So You 6 carbon can get 72 plus 6 hydrogen, hydrogen 1, 78. Okay? But I hope you recall that not all carbons are carbon 12. 99% is about carbon 12, but about 1% of carbon 13. About 1% of carbon 13. And the hydrogen, about 99.9 around is hydrogen 1. It's about 0.1% something, hydrogen 2. So now, if you look at the all benzene molecules, about 93.4% of them is all carbons, carbon 12, all hydrogen, hydrogen 1. But there's about 6% probability one of 6 carbons will be carbon 13. Because every carbon, for every carbon, it's about 1% probability in carbon 13. Okay? Natural occurring carbon, just pull carbon out of your body. Okay? Count 100 carbons, probably one of them is going to be carbon 13. Okay? And then if you look at the 6 carbon, one of them being carbon 13 will be around 6%. Around 6%. So that's why you have the about 60% of probability you have 79, because the probability of one of 6 carbons being carbon 13 is about 6%. And also you have even smaller probability for one of the 6 hydrogen being hydrogen 2. So this add together is about 60.6%. Okay? So that is why you see this peak is about 66 point, it's about 6 something percentage intensity of this one. About, okay? This is for carbon, okay? And for some other isotopes, and their use could be even more interesting. Like we know bromine, nature occurring, the isotopes, they are 79 and 81, about a 1-to-1 ratio. And the chlorine, nature occurring chlorine 35 and 37, about 3-to-1 ratio. So now we can, apply those, the isotope abundance data to help us to figure out whether we have, particular, let's say, help us to determine the composition of particular, the chemical species in the, mass spectrometer. Okay. Like here, okay, this is a mass spectrum of chlorobenzene. Okay. So the base peak here has a mass charge ratio of 112, and we assign to the molecular eye. Why? Because we know that if you have chlorine 35 in the molecule, the molecular mass of this one is 112. Okay. Just do a little calculation. You will find out. This is 112. Okay. And okay, why we so sure about, why we are so sure this molecule must be molecular eye and must have chlorine there, because it has, if it doesn't have chlorine, okay, we know nature occurring chlorine has chlorine 35 and chlorine 37, and the chlorine, the 35 to chlorine 37, the abundance ratio is 3/1. So if we have chlorine in the molecular eye, okay, we would expect a peak at 114, and that peak intensity should be roughly a third of the peak at the 112. Under indeed, we have seen that, we have a peak at 114, okay, which is 2 units higher than 112 due to the chlorine 37. And what confirmed this, this assignment is that the peak at 114 indeed intensity about 1/3 of the 112, because of chlorine 37 is, natural abundance is about 1/3 of chlorine 35. Okay, so the fact that we do see these two peaks, okay, confirm that we have chlorine in the molecular ion. Okay. On the other hand, if you look at this peak, this has a mass charge ratio about 77. Okay. I'm sure I can see that this peak comes from the phenylcation without the chlorine. Okay. Without chlorine, because of this guy. The double bond, so wrong position. Let me. I'm sure that this comes from this guy. Definitely has no chlorine inside. Okay. Why I'm saying that? If it had a chlorine inside, right? It must have a chlorine 35 and chlorine 37. Okay. Chlorine 35 is the more abundant species. So assume this one come from chlorine 35. You must, if this one has chlorine, you would have had another peak at the 79. Okay, and the peak intensity should be 1/3 of the 77 peak. Okay, if you had chlorine in this one, you would expect a peak at the 70 and mass charge ratio of 79. Okay, and that peak intensity should be 1/3 of the at 37. 77. And obviously you don't see such a peak. Okay, so that immediately gave us the assignment that this species, okay, does not have chlorine inside, because if it had a chlorine, you would expect the peak at the 77, and the intensity would be 1/3 of this one, and you don't have such a peak. Okay, so that means you don't have chlorine there. So a reasonable assignment is come from this one. The mass number match 77 and then no chlorine. It's correct. Okay, so that's how do we utilize isotope information to help us to identify the what kind of species you have in the spectrum. To know this pair, so the ion responsible of 77 peak does not contain chlorine. So most likely is the phenylcation. And although molecular ion is the kind of thing we pay most of attention to, but in many cases, the molecular ions can undergo fragmentation process, break into smaller pieces. Okay. So how do we have a hint? What kind of molecular ions are more likely to undergo fragmentation? Usually are those molecular ions, if they can form more stable carbocations, they are more likely to undergo fragmentation. One best example, if you look at this, is called propylbenzene. Okay. Propylbenzene, the molecular ion, the molecular mass is 120. Okay. And it does give a molecular ion peak at the 120. But the strongest peak, base peak, at 91. See why you would like to give the strongest peak at 91 is because if this guy undergo fragmentation lose the ethyl radical, it can give us this guy. And I hope you recall what you learned in organic 1. This is called benzenic carbocation. And the benzenic carbocation, the positive charge can be localized over totally 4 carbons. Okay, so it's a quite stable kind of carbocation. That's why you would like to undergo this kind of fragmentation process.